So we want to see what can we optimize to make the range as big as possible. So the things that we can actually change here are the initial velocity u and the angle theta. So to figure that out, we're going to have to derive an equation for the range, and then we're going to have to see how the variables u and theta affect that equation to figure out how we can optimize it best to make the ball go furthest. So we're going to start off by saying the ball starts at the coordinates 0, 0 over here, and then it ends over here, and here the x-coordinate is or, just the range, and the y-coordinate is 0, because we're back on the x-axis where we started. So now we can write down our variables. So we're going to use the equation s equals ut plus a half at squared. The final velocity isn't really relevant here, because in the x direction we have no acceleration, so the final velocity is the same as the initial, which is kind of trivial. And in the y direction it's always accelerating, so we don't really have final velocities. So we're going to say in the x direction, we're going to have u, a, s, and t. So u in our diagram is u cos theta. The reason for that is because this is the adjacent side. This side here is the adjacent side. And we know that cos of an angle equals the adjacent over the hypotenuse. So if we want to know what the adjacent is, we have the adjacent equals multiplying by h on both sides, h cos theta. And the hypotenuse is just u, the initial velocity, so we get u cos theta. So that's our initial velocity in the x direction. We have u cos theta. Our acceleration is 0, because we're going to assume there's no drag or wind or anything. Our displacement is going to be or, and the time is t, just any time t. In the y direction, we're going to have the initial velocity, for the same reason as last time, it's going to be u sine theta. Acceleration is going to be minus g, which is equal to minus 9.8. Our displacement is going to be 0, and our time is going to be t. So, out of these variables, what can we change? We can change the initial velocity, we can't change acceleration, and we can't change time. So, acceleration is 0 anyway, so it doesn't matter, but we can't change time. So we're going to try and eliminate time from the x equation. So let's just come up with an equation for x. So the displacement or equals ut is just going to be ut cos theta, and then it's going to be plus a half times a, which is 0, and then t squared. So this is just going to cancel out, and we get the r equals ut cos theta. Put a little box around that. Okay, so that's our equation for the range, but we want to get rid of that t so we can really analyze the rest of it. So now if we apply the equation to the y direction, we get that the displacement 0 equals ut is ut sine theta minus a half times g times t squared. Okay, so we can divide the whole thing by t, because the time taken to do this motion is not going to be 0, so we're allowed to divide by t. So 0 equals u sine theta minus a half gt. So now we can add a half gt to both sides, and we get a half gt. I don't know why that g is down there. A half gt equals u sine theta. We're trying to find t by itself, so we can multiply by 2 on both sides and divide by g, and we get t equals 2u sine theta over g, right? So that's an equation for time for the vertical, the y direction. We're going to sub that in up here. So we get or equals u cos theta, I'm just rearranging it to make it a bit easier, multiplied by 2u sine theta over g. So we get or equals, okay, so u times u is going to be u squared, but we want to put the constant out first. So we're going to have 2u squared times cos theta times sine theta over g. Right. So eventually we are going to want to solve for this angle, so it would be a lot easier if instead of having cos theta and sine theta, if we could just have one angle, so that's easier to solve for, or one trigonometric function. So if we rewrite this as u squared multiplied by 2 cos theta sine theta over g, well, one of the trigonometric identities is that 2 cos theta sine theta, this is the same as saying sine of 2 theta. So we can replace that with sine of 2 theta, and we get the r equals u squared sine of 2 theta over g. So here is a simplified equation for the range, and we have u, and we have the angle theta. So we're going to look at u first. This should be pretty obvious, so we can kind of rewrite this as r equals u squared multiplied by sine of 2 theta over g. So obviously, the bigger u is, the bigger the range is going to be, because just as this number gets bigger, it's being multiplied, so it's just going to get bigger. So we just want u to be as big as possible, which you probably expected. It's not very surprising. But how about the angle? So we want to see how the range changes with respect to the angle, and the way we can do that is we can take the derivative. So to make this a bit less complicated, we're going to rewrite OR as u squared over g multiplied by sine of 2 theta. So the derivative of OR with respect to theta is going to be, so u squared over g is a constant, so we don't have to worry about that for now, because it doesn't depend on theta. The derivative of sine of 2 theta, well, that's going to be, so we have u squared over g, that's going to stay the same, times sine, the derivative of sine of 2 theta is going to be cos of 2 theta, but because of the chain rule, we have to multiply by the derivative on the inside, that's going to be multiplied by 2. So the derivative with respect to theta equals 2u squared cos 2 theta, all to be divided by g. So to find a function at its maximum point, we let the derivative equal to 0, because that means it's not changing anymore, which means it's changing direction, which means that it's at its highest point, or its lowest point, depending on the function. So we're going to say 0 equals 2u squared cos of 2 theta divided by g. So we can just multiply by g, giving 0 equals 2u squared cos of 2 theta. And we can also divide by 2u squared, because u won't be 0. You can't fire a projectile with initial velocity 0. So you get 0 equals cos of 2 theta. So now we can take the cos inverse on both sides. So we get that 2 theta equals the cos inverse of 0. Which means that 2 theta equals the cos inverse of 0 is just 90. Which means that theta equals 45 degrees. So the best angle to launch it at is 45 degrees, and you want to have the initial velocity as high as possible, and that will give you the maximum range.